This is an extension to that topic where we are going to talk about acid and base properties when it comes to database selection. And it builds upon what we have learned in CAP theorem itself. So let's start with acid. So acid are itself four different properties. If you look at the definition of acid, acid is a set of properties of database transaction intended to guarantee data validity despite of any errors, power failures, or any other mishaps. So acid stands for atomicity, consistency, isolation, and durability. So if you look at first the atomicity, it actually consists of multiple things. For example, the definition of transaction itself in terms of all the properties are mainly composed of multiple operations. The atomicity guarantees that every transaction is treated as a single unit where any of these operations consist of that transaction. If they failed, we consider that is a complete failure. The entire transaction is failed and database will remain unchanged. That is what it is mentioned in this. And as it is mentioned, that the atomic system must guarantee the atomicity in each and every situation, whether it is power failure, error, crashes, doesn't matter. Let's look at the example to understand this better. So here in this diagram, we have seen that there are two friends. One is staying in Pune, Amit, who has 1,000 rupees in his account, and another one is John, who's staying in Mumbai, who again has 1,000 rupees in his account. So this case, what we are going to see that Amit want to transact or send money of maybe 100 rupees from his account, whether it is ATM or whether it is online transaction, to John, to John's account. So how this overall transaction will take place? So Amit will send 100 rupees from his account, and it will reach to a database, and from that database, the transaction or the operation will perform by adding 100 rupees in John's account. But if you see here itself, there are two operations that are happening. Like in first operation, Amit is sending the money of 100 rupees from his initial balance of 1,000 rupees, and then Amit account is getting deducted with that 1,000 rupees. Like from 1,000 minus 100, it is 900, and then John's account, who again has 1,000 rupees as initial balance, he gets the 100 rupees in his account, and then his account total value will be changed to 1,100. Just imagine a scenario where we started this transaction. The first operation happened like Amit's account deducted by 100 rupees and the overall balance has become 900. And while transacting that money to John's account, like John's account got 100 rupees and his account supposed to be added with this 100 rupees and the balance should become 1,100. So just imagine this case, if there is something wrong with the machine, like if there is a power failure, the machine crashes or anything happens. So in this case, in this complete transaction, one of the operation is failed. So that means the transaction is not fully complete. In this case, we have to revert the entire operations, what is happening here. So in this case, if the one of the operation is failed within that transaction, we have to revert even the operation that is performed on the Amit's account, that is subtracting 100 from his initial balance. So in this case, the transaction will be reverted and the data will go back to its initial state where Amit has 1,000 rupees in his account and John has 1,000 rupees in his account. So that is what the atomicity is. Now let's look at the other properties. Let me go down. So here we can see the other properties, and in acid, now C stand for consistency. The consistency ensures that the transaction can only bring database from one consistent state to another. What we have seen earlier in atomicity, that if a transaction fails, it goes back to its initial state because that was a consistent state. And if anything fails, or even if anything gets succeeded, it goes to another state, which is maybe another consistent state where transaction is completed and the values are changed in the database itself. So you can see here, I've also mentioned that consistency means any data written to the database must be valid according to all defined rules, whether it is constraint, cascade, triggers, or any of the combination. So this ensures that the data that is there in the database is not corrupt. It's not been done through illegal transaction, or we can say that halfway transaction where the data is valid in all case. So what we have seen earlier in the example where the transaction happening from Amit's account to John account. So that is, if the transaction is complete, then that will bring to a successful transaction, which will have a consistent state for the database. If it is failing, it will go back to its initial state, and then it will be another consistent state, but there will be no in-between stage. So it will prevent the database from corruption by any of the illegal transaction. The other property in ACID is durability, like ACD. So D stands for durability. I'm just jumping to another topic instead of moving to isolation. But durability is a simple thing. Like it guarantees that once the transaction has been completed, it will remain committed even in case of system failure. For example, once you have done with the transaction, the values are updated in the database. And after the transaction is finished or completed, if the system goes down because of power failure, error, or crashes, but that the information that is been updated during the transaction will remain as it is. So that is we call as a durability. So the data will be there. The data will be maybe it has already been copied in some other machine. Maybe there is a multiple machines that carry the same data, and that data is available for all other user to read and write, further read and write. This usually means the complete transaction is already recorded in the memory. That is what it's mentioning. Now let's look at the isolation property in ACID. So here, before jumping into this diagram, I would like to mention that the transaction are usually executed concurrently. That means multiple transaction, whether it is reading, whether it is writing to a table, is happening at the same time. But for each transaction to be considered as isolated, that must not interfere with one another. Meaning a transaction should not see the intermediate state of another transaction. For example, now you can see in the diagram, when Amit is transferring 100 rupees from his account to John's account, and suppose there is another operation that is happening, is that is trying to get the total from Amit's account or maybe John's account during this transaction that is happening between Amit and John, that may give an incorrect information or incorrect total because both the operation happening simultaneously. So in this case, the true isolation is that it will first allow Amit and John to have their transaction, like Amit transferring 100 rupees to John account, to complete. And once this operation is completed in an isolation, I would call it an isolation because we are allowing it to get it done first. And then the total that we're trying to receive either from Amit's account or from John's account, that operation will take place once the first operation is finished. So as per definition of isolation, it ensures that concurrent execution of transaction leaves the database in the same state that would have been obtained if the transaction were executed sequentially. So even though these operations that are happening, whether it is transaction from Amit to John or there is a total that we are going to get from both these accounts, these are actually concurrent operations. But because the state is going to change between both of these account, from Amit's account or John account into the database, it has to happen in isolation. And once the particular transaction is finished, then only we can get into the second transaction of getting an amount, the total amount from Amit's accounts and John's account. So that is what about isolation. Now let's move to the next part, which is actually talking about the implementation. Okay, so we have seen earlier where we are doing the transaction or transaction operations in isolations, but there are other implementations also. For example, locking. Locking means the transaction locks the data that is been accessed so that the database knows that it is not allowed for other transaction to modify until the first transaction succeeded or failed. So you can see in this diagram, until unless the transaction between Amit and John is not been completed or either failed, it has been locked for any other transaction, whether you want to know that the total in Amit's accounts or John's account or how many total transactions happen in an hour. So all these different transactions will not be able to access the information that is happening between Amit's and John account. So until unless it is not succeeded and failed, the next transaction will not able to access that data. So it is locked and it's not allowed other transaction to modify anything in this. And this lock must be acquired before processing the data. Whether even it is reading of data, not just writing, even if we are trying to read, the lock must be acquired before processing. Okay, that's one way of implementation. There is another way, it's called multi-versioning, where database itself is having multiple versions. Like database provide for each reading transaction the prior and unmodified version of data. So that is being modified by another version at the same time. Maybe we are working on one version where Amit and John are having transaction with one another. Like there is a account information that is changed between them. So that is one version. But that information is a different version, and the another version will be provided to the other transaction where we are trying to know that how many total transaction happen in an hour or maybe the total amount in Amit's and John's account. So that will be provided. So it will be two different versions of the database itself. So what exactly purpose of this multi-versioning. This allow reader to operate without acquiring a lock. Here now we can see that the lock is not needed in this multi-versioning. And that is the writing transaction do not block reading transaction because there is a modification happening between Amit and John. But here we just want to know the total transaction or the total amount that is in Amit's account prior to what is transaction that is happening right now. So this will not, this is just a reading operation. So it is not going to get blocked because some writing operation that is going on. So that is where the multi-versioning is useful. And the last is distributed transaction. This is very important. In a distributed transaction across distributed databases, like across multiple places in the network, where no single node is responsible for affecting the data by the transaction. This brings an additional complications where network connection fail or one node may be successfully complete its part of the transaction and then required to roll back to the previous state because of some failure of some other node. So that is possible. So this is an additional complications. In this case, there's something called two-phase commit protocol provides atomicity for distributed transaction. This ensures that each participant, whether it is node, whether it is database, in the transaction agrees on whether the transaction should commit it or not. So the participant means how many nodes are involved for that particular transaction, whether it is one node, two node, three node, those who are taking care of the transaction, they all should agree that yes, we are done with our task. And now we are agree that transaction should be committed, or yes, one of the node is failed. That means the transaction should not be committed. That decision will be taken care. So this is how we handle the distribution transaction. Now let's look at the base properties. Base stands for basically available, soft state, and eventually consistent. Basically available ensures that data is written regardless of any freshness. In the sense, you will not get the latest data when it is you ask the database for any kind of information. So in that case, whatever data is available with the database, it will be given back to the user who is requesting. So even though data is available, that data is available through because it is spread across multiple nodes of the database cluster, and the base database do not force immediate consistency. Means the data is not updated so far. Whether one node is updated, another node is not updated, and if someone is requesting to that other node for the data, you will get the not latest data, but the data prior to it. So that is what the basically available. That means you will get the data whenever you send a request, but the data may not be the latest data that has been updated. Soft state is actually indicates that the data is not fixed rather than fluctuating, reflecting the concept of eventual consistency. Means the database don't have to be right consistent, nor do the different replicas that have mutually consistent all time. So these values keep on changing. Soft state stands for it is mainly not fixed. The data state is not fixed. It is changing over the period of time, like eventual consistency. It will change after some time, and then once the request later some request comes, it will get the latest information. But at this point of time, the data is going to change over the period of time. Okay, and then it comes eventual consistency. Again, here, as I mentioned, database exhibit consistency at some later point. Means the data is going to get updated later in the later stage once the information is replicated through all the nodes and the data will be available. So you can still read the data as it is mentioned here. Until the latest information is not updated, data reads are still possible. You can still read the data, but data may not be latest data you will get it. Okay, so that is the whole purpose of this base properties. It is available, so whatever is there, you will get it. It is soft state because data is going to change over the period of time, and eventual consistency means data is again going to change, but reading is still possible. You'll get whatever is there. Okay, but I just mentioned here a note that given base properties that lose consistency, the developer should be very knowledgeable about consistent data and careful about that consistent data. Okay, so that is just note that I've added. So these properties are not strict properties, and that's why there's a different purpose for it. So let's look at some of the quick example. So here I mentioned ACID versus base. It's just in terms of usage or the database itself. If you look at the Cassandra, Redis, MongoDB, these are all example of NoSQL database that follows base principle, where the data will be eventually updated in the database. You will not get the latest information all the time. It is available, it will serve you, it will serve the user request, but the data may not be the latest one. But if you look at the ACID principle, they are usually followed by the SQL databases, where you will get the consistent data, where you will have strong consistent data, where you will get the latest information always. But maybe it's sacrificed on availability sometimes. So the choice between ACID and base database depends on the specific data requirements of the user. So that's why I just mentioned some use cases for the database. So you can see that relational database are essentially for financial institutions. I mentioned earlier in my earlier videos that because they need data consistency. So the financial transaction, institution, or any kind of information where it must have the consistent data. So in that case, we use relational databases, and for NoSQL database is mainly preferable for messaging apps where data availability is prioritized over consistency, allowing for a quicker scaling. For example, what we have seen earlier, the YouTube number of views, number of likes, if you want to see, that is updated over the period of time. It's not immediately updated that someone liked and you get that count. No, it changes over the period of time, and where because that number of likes or number of views are not that important for the user. So that is the example of ACID and as well as base databases.